Thank you very much for this nice introduction. Yes, well, first let me draw your attention to this. I've given this talk many times, and it has been published several times in proceedings, but you know, these proceedings books are not so easy to find out. And so I decided recently to send it to QuantFiz, and I mean to the server, to the archive server, and I find it's a very good use of the archive server to put this kind of papers that you can find only in rare books, okay? So, let me first put this in a perspective that I have realized only recently. 2 years ago, Cambridge University Press asked me to write an introduction to the second edition of the famous collected papers of John Bell, Speakable and Unspeakable in Quantum Mechanics, and I really recommend you buy it. It's cheap, it's very good. And I will get some royalties on my introduction. Only a small fraction of the royalties. And while writing this introduction, it became more and more clear to me that I could argue that starting in the 60s, there was a new quantum revolution. What do I mean? We all know the first quantum revolution, which was first a conceptual revolution, mostly based, as a naive physicist, on wave-particle duality, and it first allowed us to understand matter, to understand interaction, to understand the interaction between matter and radiation, and later, decades later, it gave rise to a real technological revolution based on transistor, integrated circuits, and laser, and it is what we call information-based society. Well, I would like to argue that in the 60s, a new quantum revolution emerged based on two ingredients. And the first one is the fact that people began to seriously apply quantum mechanics to single objects, not only in textbooks, but in real life. Previously, I want to argue with you on that. Yes? I'm ready to argue.
Quantum mechanics to electrons.
I think, well, many people were thinking that quantum mechanics was applicable only to ensembles, calculating average values of this, of that. And there were these fantastic experiments in the 60s and 70s on a single trapped electron by Demelt, single trapped ion where people could see for the first time quantum jumps. Before that, you had not seen a quantum jump with your naked eye. Single photon, single atoms with a scanning tunneling microscope, etc. And then people began to think more, and they developed what we have in quantum optics as quantum jumps, treatment, quantum Monte Carlo, etc. This was applying quantum mechanics to single microscopic objects. Now there is all this exciting domain of trying to apply quantum mechanics to macro or at least mesoscopic objects, and I think this was mostly the talk of Tony yesterday, okay? The second ingredient, I think, for this second quantum revolution or new quantum revolution is that entanglement was recognized as something completely different from all the extraordinary features of quantum mechanics we already knew. And this had been advocated by Einstein, Podolsky, and Rosen as early in 1935, but I think really that it was recognized by a majority of physicists only after Bell's theorem and Bell's inequalities. Will this second quantum revolution or new quantum revolution lead to a new technological revolution? Well, we don't know yet, but if it was the case, it would be on quantum information. So my talk will focus on this second ingredient of the new quantum revolution, that is to say, entanglement. So I will briefly describe the Einstein Podolsky Rosen situation and the debate between Einstein and Bohr, then present how I understand Bell's theorem, and this is where my title applies. It's my naive view of Bell's theorem, okay? Then I will make a brief review of the experiment, and we will try to find a conclusion. The Einstein-Podolsky Rosen original equation was, can quantum mechanics be considered complete? And more specifically, the problem is the following. Is it possible to explain the probabilistic character of the prediction of quantum mechanics by invoking an underlying world where we have well-defined supplementary parameters that people like to call hidden variables, okay? This was suggested by the reasoning of Einstein, Podolsky, and Rosen that I will develop a little bit, and they even thought they had demonstrated that it was necessary to explain the probabilistic character of quantum mechanics with hidden variables, or at least with an underlying level. Of course, Bohr, everybody knows that Bohr didn't agree with the conclusion of Einstein, Podolsky, and Rosen, and the next breakthrough was 30 years later in 64, 65, when Bell allowed to give an experimental equation to this conceptual debate. So let me describe the Einstein, Podolsky, Rosen Gedanken experiment. It is not the original scheme, but it is a scheme on which the experiments are based, and I rather explain it that way. In fact, David Bohm designed such a scheme. It was a Gedanken experiment since at that time, and he designed that scheme with spin 1/2. And if you don't like polarization of a photon, you just in your mind think that you are measuring the component of a spin 1/2 along a certain axis with a Stern and Gerlach magnet. So here I have a photon traveling to the left, arrives on a polarizer, and it can goes out either on the +1 channel, and then I say that I have found the polarization along A, or it goes out in the extraordinary channel that I label -1, and I say that the polarization of the photon has been found orthogonal to A. And again, if this was a spin 1/2 particle and this is a Stern-Gerlach, you would say that this is up along axis A and this is down along axis A. You do a similar measurement on another photon going along the other direction, and you can use single photon counters here, 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 and with these single photon counters you measure probability of detecting your photon in this channel, and most interesting, you also can measure joint probabilities of detecting one photon here and one photon here for a certain set of orientation. The Einstein-Podolsky-Rosen situation will happen as soon as you have a polarization state of this form. What do I mean by this form? X is an axis perpendicular to propagation, so that state, XX, would mean two photons polarized like that. That state, YY, would mean two photons polarized like that. The interesting feature of this state is I cannot wave hands and to tell you what kind of polarization is this state. Because this is an entangled state, a state that you cannot factor as a product of a polarization describing the first photon and another state describing the polarization of the second photon. So the major property of this entangled state is the fact that you cannot factorize it, and now I cannot tell you the first photon is polarized like that and the other one polarized like that. It's quite easy to make calculation of the prediction of quantum mechanics for the various outcome of the measurement of polarization you make. It's really a beginner calculation in quantum mechanics. For instance, you can calculate what is the probability to detect +1 if I measure only polarization of this photon. And the result is quite trivial. I get, with the same probability, +1 or -1, whatever the orientation of this polarizer, which means from this point of view, it's just like natural light. Happens at random, +1 or -1. Same prediction when you consider the second photon on the other side. Now what is more interesting is to calculate the joint probability. For instance, P++ of AB means probability to find +1 here and +1 here with orientation A for the first polarizer, B for the second polarizer. This probability is 1/2 of the square of the cosine of the angle between the two polarizers, okay? Now, Jora, sit down, please. Thank you. Now, the point is that as soon as you have obtained this result, it's clear that you have strong correlation between the result here and there. take the example of two polarized aligned along the same direction. The angle has a value of 0. Then you find that P++ equals 1/2. But remember that P+ has also the value of 1/2. This means that the conditional probability to find +1 and +1 here, if I get +1 here, this conditional probability is 100%. It means that I can either find +1 or -1 here, but if I find +1 here, then I am sure to find +1 here, and if I find -1 here, I am sure to find -1 here. This is indeed a strong correlation. Well, just a small technical point. In order to quantify this correlation, we introduce a usual correlation coefficient defined in an absolute classical way. I say I have here a random variable with value +1 and -1, here a random variable with value +1 and -1, and the correlation coefficient will be average of the product minus the product of the average and normalized, and it turns out that it comes to this quantity. And if now, in this definition, I introduce a prediction of quantum mechanics for that state, I find that the predicted correlation coefficient, as predicted by quantum mechanics for this EPR state, is cosine of 2 times the angle between the polarizer, which means that for a null angle, the correlation coefficient is +1, total correlation. For 90 degrees, the correlation coefficient is -1, also total correlation, but just +1 and -1 happen together, etc. Okay, this is prediction of quantum mechanics. Now, I have a theory which predicts strong correlation. Can I understand this correlation? Can I make an image? Well, of course, the most normal way of doing it is to take the set of equations I have written to reach this result and try to make an image out of it. The most efficient way of doing the calculation is just to consider the outcome of the experiment, the eigenvector corresponding to the outcome of the experiment, project the initial state vector on it, square, and you get it. But the problem is that it is very hard to make a picture in real space, because that state vector operates in a space which is a tensor product of description of the first particle and description of the second one, and it's quite difficult to make images in such a state, and you would like to make a picture in real space. And so there is another way of doing the calculation, and I should insist that this calculation is absolutely standard quantum mechanics. Okay, you take any good book of quantum mechanics, for instance, my favorite, guess what it is, it's a French one, and you just follow the rules, right? There is nothing special in what I say you. But you just imagine for a while that this polarizer is a little closer to the source than the other one, so that you have a first step, you do a measurement at polarizer 1. So what can you get? Well, obviously you can get either +1 or -1. Let's assume we get +1. If we get +1, just after the result, we have to project the initial state vector on the eigenspace corresponding to that result. And the result of this projection is that you go from this state to a state which is now not an entangled state. It's a state where the first photon is polarized along A, normal. This is what I have found as a result of measurement. And the other one is polarized exactly along the same direction. But let's suppose, let me finish with the reasoning, and then I have the second photon which is polarized along A. Now I measure it with a polarizer along B, and it's just a Malus law that gives me the result. So the result is the same. Now let's suppose that the first measurement gives -1. Then the projection of the state vector tells me that immediately after this measurement, now I get minus for A and minus for B, which means that the first photon and the second photon will be found with a direction of polarization perpendicular to the direction A. And then I am in serious trouble, because the picture that I am deriving from this calculation tells me that the polarization of photon nu2, that can be very far away, This polarization instantaneously changes according to the result of measurement that takes place here. That's the kind of image that I build if I try to derive an image from this calculation, which again is absolutely standard quantum mechanics. Of course, Niels Bohr told us you should not try to make images, but I am a stubborn and naive experimentalist. I like images, and so the question is, can't we try to make a more palatable image? And of course, there is a very simple image. The simple image is the following. It could well be that from the beginning, the two photons, nu1 and nu2, share some common property that I name lambda that will determine the fact that the outcome will be, for instance, +1 and +1. So there might be pairs from the beginning, it would be +1, +1, so you get +1, +1. Then other pairs, -1, -1, and then you get -1. And so this image allows you to understand correlation at a distance. So this image is very simple, very nice, but you have to realize that by doing so, you complete the formalism of quantum mechanics, you introduce supplementary parameters. Why do I say that? Because, for instance, in my very simple explanation, I said some pairs from the beginning are ++, other pairs from the beginning are --. So I introduced two different kinds of pairs, which in the formalism of quantum mechanics are all described by the same state vector. So I introduce a lower lying level, I do introduce supplementary parameters. And this was the essence of Einstein Podolsky Rosen reasoning. Now, Bell's theorem. Well, Bell's theorem basically takes seriously the idea that you should try to make a sense of this correlation by introducing common causes from the origin, from the source. So the formalism is extremely simple. You introduce a set of parameters, whatever mathematical object it is, which is common and shared between the two photons where they are of the same pair when they are prepared in the source, and then they separate and fly away. Now when photon nu1 arrives at this polarizer, it bears the supplementary parameter lambda, and there must be some kind of mechanism giving the outcome either +1 or -1 if you have put the polarizer in orientation A. So that means that in your formalism you must have some kind of two-valued function which is a function of lambda and of the orientation A and can assume only the value +1 or -1. And similarly, of course, for photon nu2 that goes the other way, there must be some kind of function with two values. Of course, in order to have a complete formalism, you must also describe how the various parameters lambda are distributed over the pairs in the preparation. So you introduce a density of probability, which is positive and normalized. Nothing special, makes sense, right? And now, if you decide to invent a particular hidden variable theory, as soon as you have an explicit form for your quantity capital A, capital B, and rho, it's trivial to calculate the prediction for the various probabilities for your hidden variable theory. For instance, obviously, this is the probability of having +1 here in orientation A. You see, this is 0 for -1 and 1 for +1, so it's the average value of variable which is 1 here and 0 here, so it's a probability here. And skipping details, it's quite obvious that the correlation coefficient, which is the average value of this random variable and this random variable, or rather the average value of the product, this will be the correlation coefficient in your particular hidden variable theory. I like very much this naive example. The examples go along the following line. We accept the idea that when the two photons, it's a classical idea, when the two photons are emitted, they have a well-defined linear polarization. There is a plane, a common plane of polarization for the two photons, and the angle of this plane to the vertical direction is just lambda. So lambda is just an angle. And because I want to have rotational invariance, I will, in my model, assume that all the directions are equally isotropically distributed, so this is density of probability I introduced for lambda. Now, I have to invent a sensible function for giving the result of the measurement here. And this looks a little bit strange, but it's very sensible. Look what is the result of this function. This function tells you that if the direction of the polarization of the photon is parallel to A, you find +1. If it is perpendicular, you find -1. And the borderline is just at 45 degrees. This is a virtue of this function. So nothing not reasonable. It's the most reasonable model you can invent. And now, you just work out the prediction of this model, and you are very happy because you recover most of the prediction of quantum mechanics. Single probabilities are 50%. Correlation coefficient is total for parallel polarizers. It's total for perpendicular polarizer, etc., etc. So you are very happy. So you work out in detail the etc., etc. And this is what you get. The blue line is a prediction of quantum mechanics. The red line is a prediction for your naive hidden variable model. And you say for a first try, not bad. You know, it's really very simple. So you say, I'm going to pay a visit to my theorist friend. He knows so many special functions and things like that, that probably it will be very easy for him to find a model which will fit at all points the prediction of quantum mechanics. So, is it possible? Well, the answer is given by Bell's theorem. I think Bell's theorem is nothing else than the answer to this question. That's no. The essence of Bell's theorem is that there is no way to sophisticate the model to the point where the local hidden variable model would adjust on all points to the prediction of quantum mechanics. You can reproduce some prediction of the quantum mechanics, but not all the prediction for all angles. So how does it work? Starting with a model like the kind of model I have given to you, but in a general form, not assuming a precise form, but in its most general form, Bell can show that there is a certain quantity S which is restricted to be -2 and 2. And if you ask me the question at the end, I can show it to you. It's very simple algebra, but just it would stop my explanation. It's 2 minutes of very simple algebra to make the demonstration that this quantity should be between -2 and 2. What is this quantity? It's a combination of 4 coefficients of correlation with 2 sets of angles on one side, A and A prime, 2 sets of angles on the other side, B and B prime. So you measure AB, AB prime, A prime B, A prime B prime. You put the numbers into this quantity, and if you can describe your correlation by a hidden variable theory, then this quantity should not be larger than 2 or smaller than -2. Yeah, it's not a mistake. It's a genius intuition. That's Bell. Huh? I will show you. I will show you at the end. I would prefer to continue. On the other hand, quantum mechanics. I remind you the prediction of quantum mechanics for the EPR state, and let's take a particular set of angles. A, B equal pi over 8. B, A prime pi over 8. This one pi over 8 also. So cosine of pi over 4 is well known, is 1 over root 2. So here you get 1 over root 2, 1 over root 2, 1 over root 2. Now A, B prime. A, B prime, double, and the cosine is minus 1 over root 2. So here 2 comes plus 1 over root 2. And the result is 2 root 2. And 2 root 2 is obviously bigger than 2. That's Bell's theorem. Bell's theorem is this, and then it's enough to have one counter example to show that there is no hidden variable theory that can reproduce this particular result. So we have a conflict now. So the possibility of completing quantum mechanics with hidden variables is no longer a matter of taste between Einstein and Bohr. it has become an experimental question. So it's a question for naive experimentalists. But before doing the experiment, as somebody said, better to check the fuse last time, okay? Before throwing the baby or the apparatus. So what are the hypotheses for Bell's inequalities, that is to obtain a conflict with quantum mechanics? There are hundreds of papers in the literature about that. So probably if some of you is very emotional about that, he will not fully agree with me. It seems to me anyway fair to say that there are basically two fundamental assumptions you must make to obtain Bell's inequality. The first explanation is that you insist on understanding the correlation at a distance by invoking a common property shared by the two photons from the beginning and then carried along with the photon. This is what Einstein called physical reality. Einstein would say, once the two photons separate, each brings a physical reality, and this physical reality has been determined by the initial conditions. Second hypothesis I did not mention yet, but Bell mentioned it as very important in his famous paper, that locality. What do we mean by locality? You remember when I introduced this function describing how this polarizer reacts to the photon, I wrote that the result of the measurement depends on the hidden variable carried along by this photon, but also on the orientation A, but not on the orientation of the other polarizer, which is far away. And similarly here. And also, I wrote that the way in which you prepare the pairs in the source here does not depend on the orientation of the apparatus that will later perform the measurement. This hypothesis is crucial. If you try to build a hidden variable theory starting from quantum mechanics, you would like to write non-local quantities. So writing local quantities is crucial to find a conflict with quantum mechanics. And so people would say that Bell's inequality holds for any local hidden variable theory or for any local realistic or realist, I don't know how to say, theory. Now, some comment about the locality condition. So this condition that what happens here should not depend on the orientation there. It was stated as a reasonable assumption, but as said and written by Bell in his first paper, after all, there is no basic reason that prevents some unknown interaction to provoke an influence from this orientation on the result of the measurement here in a static experiment. But if I could do an experiment in which the orientation of the polarizer are switched fastly at random. By fastly, I mean in a time short compared to the time of flight of light between the two polarizers. Then it is relativity which would prevent the orientation of this polarizer to have any influence on the result here. And of course, it would even more prevent any influence on the preparation of the source, on the photon on the source which have been prepared before. It would go against time flow, okay? So in such an experiment, the locality condition would become a consequence of Einstein's causality, which says that there are no faster than light influences. And so to conclude, if you have an EPR state, on the one hand, the quantum mechanics predicts this, and on the other hand, Bell's inequality tells you that if you can describe the world by a local realistic model, that is to say a model where the correlation are related to the initial joint properties of the photon and then they bring it along, then there is a conflict between these two images. And so the next question is, what about nature? So I like to put Bell's theorem under this form. Some prediction of quantum mechanics, and mostly in the Einstein Podolsky Rosen situation, cannot be mimicked in a reasonable classical-like model in the spirit of Einstein's idea, because I invoked Einstein 2 times, first time to complete quantum mechanics, and second time for enforcing the locality condition. Now what is interesting is that in 1965, when Bell's theorem appeared, in spite of decades of experiments agreeing with quantum mechanical prediction, there was no experimental result available for testing Bell's inequality versus quantum mechanics. And so, reasonably enough, or crazily enough, some people thought that maybe the violation of Bell's inequality was an indication of a limit of the validity of quantum mechanics. Why not? So, experiments started. First experiments in the beginning of the 70s were done, or even end of the 60s, 19, not 18. I say that for young people. So experiments with gamma photon produced in disintegration of positronium. There was also an experiment in Saclay with protons by some scattering on a target, etc. The result of this experiment was an agreement with quantum mechanics, but it was not really a test of Bell's inequality for the following reason. To make a test of Bell's inequality, you must be able to make a two-value measurement of the polarization. And there are no such polarizer for such photon. For such photon, you do a scattering experiment, which gives a continuous random of result, and by using the Klein-Ishina formula, which is a quantum mechanical formula, then you can say, if I had an ideal polarizer, this would be the result I would have. So you use quantum mechanics to test quantum mechanics. It's a kind of circle. So there was a famous paper by Clauser, Horn, Shimony, and Holt in 1969 that demonstrated that you can make a state like that by starting from an atom excited to a state, an upper state, with angular momentum J equals 0. And then if the atoms decays but what we call a radiative cascade, emits a first photon to a momentum to a state with an angular momentum +1, and then goes to the ground state with angular momentum 0. If in addition you select one photon going to the left and one going to the right, and they have different wavelengths, so you can put color filters here, then it's not very difficult to demonstrate that the state of polarization you get is exactly the one you would like to have to make your test. And the good thing is that with visible light, and this gives visible photon, we indeed have polarizers. I mean, spath, how do you say, calcite. Calcite was discovered well before people knew what is the polarization of a photon. As a matter of fact, it's an empirical fact, you have a piece of matter that gives you a two-value measurement. An interesting remark, I think, from my point of view, before doing an experiment like that, you say, what is a prediction of quantum mechanics if the experiment is not ideal? For instance, no experimentalist, of course, likes to have very small holes here. He would like to prefer a large aperture lens to collect a lot of light, have a better signal-to-noise ratio, etc. What happens if you have a big angle here? Well, the result of the calculation is that the predicted correlation, according to quantum mechanical calculation, are smaller. Now you ask a question. If instead of having a nice scheme like that, there is a nuclear spin in my atom, so that there is an hyperfine structure here, and I do the full calculation, what happens? The result is that the prediction of quantum mechanics is that the correlation coefficient will be not large enough to violate Bell's inequality. So from the beginning, quantum mechanics tells you S will not be bigger than 2, so there is no point in doing the experiment. So the point I want to make is that any computable extra effect, badly controlled effect, leads to a decrease or even a cancellation of the conflict between Bell's inequality and quantum mechanics. So the experiment must be as ideal as possible. The first generation of experiment was carried out in 72 and 73, one in Berkeley, one in Harvard. Guess what was the result? One was in favor of quantum mechanics, and the other one was in favor of Bell's inequality. It was an interesting time. The point is that the signal that you had in this experiment was so weak that you had to average out results for weeks. And it's very difficult to guarantee that there is no drift in your experiment for such a long amount of times. In 1976, at College Station, Texas, Fry and Thompson designed the first experiment using a laser. And then, rather than accumulating data for hundreds of hours, they only had to accumulate data for hours, say. Okay? And the signal-to-noise ratio was much better, and the result was clearly in agreement with quantum mechanics. But these experiments were still very far from an ideal experiment. And so at that same moment, we decided to enter the game and to use the recently developed technique of two-photon excitation by adding two layers of photon in a nonlinear effect, exciting directly the upper level of the cascade. Before, what people were doing is exciting with a classical source upper lying level, and then it would decay by many different routes, and only once in a while it would give you the pair of photons you want. Many often it would give you several photons plus this one, but without its twin brother, etc. With this nonlinear process, you excite the atom here, and then the atom has no choice. It can only decay and delivering the pair of photons you are expecting. And with this new source, just to give you an idea of the progress, we could now achieve 1% accuracy on the measurement of coincidence detection in 100 seconds. Remember that the first experiment were 100 hours, then the next experiment was 1 hour, and now it's 1 minute. And it totally changed the life of an experimentalist. This is just to show you that it was a true experiment, okay? So in this experiment, we were still using a non-ideal scheme in the sense that at that time we only had polarizer giving the result +1 but not giving the result -1. And at this point I like to tease theorists, so I think it's a right place to do it. When you come to a friend theorist and tell him, look, I am annoyed because my polarizer gives the result +1 and just absorbs the photon when it is result -1. What should I do? And your friend theorists say, it's very easy, my friend. If you observe something, it's +1. If you observe nothing, it's -1. And you first laugh, and then you think, well, after all, theorists are smart, so I should think a little more. And after a while, you realize that he is quite right. If you compare what you get with the polarization in station here, with what you get removing the polarizer, then it's likely that the difference is the result -1. So this was the idea of this first experiment, and we redid an experiment in that style, but with our beautiful source. And what we got was a very clear and definite agreement with quantum mechanics, a violation of Bell's inequality by 9 standard deviation, much better than any previous violation. And the most important result, I think, for this experiment, which was really a new result, which is the following. When we pulled the polarizer far away from the source, the correlation was still there. And this was answering a debate. Some theorists had argued it was the so-called furry hypothesis in the literature, although I think it's unfair because furry was of the opposite opinion. But anyway, it's called the furry hypothesis in the literature. The furry hypothesis is the fact that, okay, at small distance you are going to observe the EPR correlation, but if you go far away, it will be disentangled. The linear superposition will turn into a mixture, and you will no longer have this correlation. So if you ask to an advocate of this kind of position, but what is the correct scale, length scale? How far should I pull the polarizer? And after a while he comes and says, well, probably the coherence length of the photons. So here the coherence length of this photon was 1 meter, a little more than 1 meter. So we pulled the polarizer at 6 meters and the correlation was still there. Then we could do an experiment which I think is really very, very close to the ideal experiment. In this experiment, we could build true two-channel polarizer. So we get the result +1, we get result -1, both can be detected, and here we have a 4-fold coincidence system. That means that in a single run, lasting only 100 seconds, we get these 4 numbers, and in a single run, we directly get the correlation coefficient with a self-normalization. That means that we don't have to care about stability of the experiment. In previous experiment, you must compare successive measurements. And then if there is a drift in between, it's a major problem. Here, in a single run, you measure the 4 numbers and you divide by the sum. Here you have this minus, minus, and plus sign. But here you have the sum, and it's a self-calibrating experiment. So I think it was really very close to the ideal experiment. And indeed, here you have the result. Here is a quantity S that you want to test against Bell's inequality. And you see that this quantity S versus some angle between the polarizer starts from 2, goes to a maximum value of 2 root 2, will go to this other value here. The green line is a prediction by quantum mechanics taking into account the slight inefficiency of the experiment, and the red points are the points that we did measure in the experiment. The agreement really, I shouldn't say shocked me, but impressed me really very much. And then we obtained a violation of Bell's inequality by more than 40 standard deviation, achieving a quantity S of, it's here, close to 7, in agreement with the quantum mechanics prediction, and very close to the maximum value in an ideal experiment of 2.8. Okay. Then we really wanted to enforce locality by switching rapidly the polarizer. But you have to realize that these are heavy objects, like 50 kilograms. It's not so easy to turn in a few nanoseconds, okay? So our trick was the following. Instead of trying to turn the polarizer, we add a switch here, an optical switch which is able to redirect the light either towards this polarizer or towards this polarizer. And then you can detect here, and if this switch rapidly goes from one position to the other one, this is equivalent to a single polarizer rapidly switch from A to A prime to A to A prime, right? So we do it on this, also on the other side. And just to give you an idea, the switching period was of the order of 10 nanoseconds, so every 10 nanoseconds we change the orientation. The distance between the two ends of the experiment was 12 meters. It takes 40 nanoseconds for the light to travel from one end to the other end. So clearly the switching period was smaller than the time of travel of light between the two ends, so we enforce space-like separation for these events. There was a drawback in this experiment, but remember it was more than 20 years ago and it's all we could do, is that the switches were quasi-periodic switches. We could not implement real random switching for fundamental technical reasons. Anyway, we were not stupid, so we were driving the two switches with two different generators, not working at the same frequency, and drifting independently. So in a sense, we had independence, but it was not random. This experiment was much more difficult. The signal-to-noise ratio was less, and to make a long story short, there is a special expression for Bell's inequality that according to hidden variable theory, delta should be negative, and we found it positive by 6 standard deviation, and we had a good agreement with the prediction of quantum mechanics, and this is just some indication of the quality of the experiment. So this was not an ideal experiment from several points of view that I will slightly okay, I have another 10 minutes, yes, on which I will slightly comment. Well, I just quote here an experiment in 1985, which was a beautiful experiment from the point of view of atomic physics, but not very significant for Bell's inequality. But the real breakthrough was what happened in the late 80s when people began to use what we call parametric down conversion to create pairs of photons by some kind of nonlinear process. Why is this a nice process? It's a nice process because the direction of emission are well enough controlled that you can feed this photon into optical fibers. So you will see well, we could not do that. So with this kind of source, they have found a perfect correlation. Just to quote one result, in the group of Zeilinger in Innsbruck, they could violate Bell's inequality by 100 standard deviation. Okay. They broke our record. Good. And they have tested other variables like time, energy, position, momentum, rather than just polarization. But of course, a major advantage is the use of optical fiber, which allow for large distance test, I will show you, and also experiment with now fully random polarizer, enforcing strictly the locality condition. And this is just an illustration. This is the experiment of my friend Nicolas Gisin in Genève. Nicolas Gisin is smart enough to be able to use the commercial network of optical fibers of Swiss Telecom. He is allowed to use it, and he has tricks to use it, and so we can make an experiment where non-locality, or call it as you want, entanglement, is tested at the distance more than 10 kilometers. The source is somewhere in Bellevue, and one detection is here, and the other one is here, or something like that. So this Innsbruck experiment by Zeilinger, they finally could make an experiment in which you launch a photon in the optical fiber, and while the photons are in flight, you make at random a decision of the orientation, and you monitor everything, and then at the end you compare and you do the ultimate test. In fact, it's not totally ultimate because of some loophole that some people think is important and others think it's not important, but as soon as there is a loophole, it would be better to close it. The detection loophole goes along the following line. The photon detectors that we use do not detect 100% of the photon. As a matter of fact, they detect only 20%. So 4 out of 5 photons escape to your attention. And some people design far-fetched, I would like to call them, hidden variable theory, taking advantage of this lack of efficiency of the detector to say, well, if you could observe all the photons, yes, indeed, you would have a violation of Bell's inequality. But there is a conspiracy of nature that it takes advantage of the fact that you lack some photons to fool you, etc. So Bell was not excited by this reasoning, because he was saying, I don't see why the law of nature should change suddenly when the efficiency of a detector crosses a value of 70%, while there is absolutely no fundamental law preventing you to have a detector with an efficiency of more than 70%. Now we have detectors with efficiency bigger than 70%. Anyway, the most convincing experiment from this point of view has been done by Dave Wineland in Boulder, where using completely different variables, using trapped ion, he can make experiment with 100% detection efficiency, closing the detection loophole. The problem with this experiment is that the two ions are very close from each other, so we cannot enforce the locality condition. So the ultimate experiment would close the detection loophole and enforce locality, and it has not yet been done. So I can tell you, if you write a project to NSF for doing an experiment like that, and if I am a referee, I will be strongly in favor. I will support it, provided that it is meaningful, of course. I think it can be done, so one has to do it. So let us conclude now. Entanglement has been evidenced as an experimental fact. And I would like to argue along 2 points. First, that entanglement is well known now as a resource for quantum information, and I will come back to the conceptual problem and the discussion between Einstein and Bohr. First, the fact that entanglement has given rise in the last decade, let's say, to all this wonderful development of quantum information. And just, I don't want to go into details, but the idea of quantum information, most of you know it, is that if you base your processor on different principles, on different physical principles, then you can implement different information processing scheme. And Rolf-Landauer had insisted that information is physical, and if you have a different physical system, it might be different. And at the moment, there are really two different lines of application of entanglement in quantum information. One is quantum cryptography, that's the distribution of a secret key between two partners, and the very principles of quantum mechanics allow you to be sure that there was no eavesdropper on the line, that your two keys are really not shared by a third party. This really works. What does not work yet is quantum computation. It has been demonstrated, you all know that theoretically, that the complexity of a problem would be dramatically reduced, for instance, factoring into prime factors. The time, well, there is an example which is absolutely fantastic in the course of Preskill that you can download from the Caltech the Caltech lecture notes. Okay, it gives an example where, to factoring a certain number, the kind of scaling that you would have with a quantum computer means that a calculation that would take the age of the universe with a classical computer would just take 1 year with a quantum computer. This gives an idea of the scale. Of course, this has not been implemented instead of a lot of progress, but very far from a real implementation. So I would like now to concentrate in the last minutes on what have we learned from the violation of Bell's inequalities, that is to say, the demonstration that yes, entanglement is as bizarre as Einstein has pointed out. Well, we can conclude that there is a failure of the local realistic view of the world a la Einstein. Einstein, in fact, had written that if what he was saying was not correct, and we know nowadays that it's not correct, but he was just using this argument as an ad absurdum reasoning. But he had written that if what he said was not correct, you would have either to drop the need of the independence of the physical reality present in different parts of space. And by different parts of space, he means separated by a space-like distance. Or accept that the measurement of a first system can change instantaneously the real situation of the second system by some kind of telepathy, right? And of course, Einstein didn't like that. We have to accept one of these two hypotheses. In my opinion, what we have to accept is that the image where you have well-separated entities in space, which are really independent, this image has to be dropped. What I mean is that I don't think you can cut in two parts. On the one hand, the hypothesis of a separated reality, and on the other hand, the hypothesis of locality or non-locality. Because if I have two separated reality, but that they can interact instantaneously with each other, I don't understand what it means that they are separated. So it means to me that it is a global hypothesis, and this global description à la Einstein, we have to renounce it. But at this point, in case there are some journalists in the room or if it goes on the air, I would like to insist that even with such a strange property of the real world, we cannot signal faster than light. And if you give me 2 minutes, I like to show it. You have here two people, some call it Alice and Bob. I prefer to call them Arthur and Beatrice. Okay? And the idea is the following. Arthur will change the setting of this polarizer rapidly. Can Beatrice know instantaneously that he has changed the orientation? If Beatrice only looks at her own result here, +1 or -1, we know that she gets 50% probability of +1, -1. There is no information about A. But if she can get an information about joint detection, then she will see an instantaneous change in the joint detection. Does this allow for faster than light signaling? Of course not, because to know that the correlation coefficient or that the joint detection have changed, she must get an information from Bob or from, Arthur, telling him, I got +1, and then she finds she has -1, and to evaluate the correlation coefficient, she must get the information from the other party, and the other party must use a normal telephone to send the information, so it cannot go faster than light, okay? And this, of course, reminds us, but this kind of demonstration was known long ago, but this reminds us of the role of classical channel in quantum teleportation and the fact that quantum teleportation cannot go faster than light. Okay, so once you realize that, you can say, so, there is no problem. Why did we bother to spend 1 hour listening to this guy? There is no problem. Well, let us have a different look at the experiment. We consider it from far and a posteriori. We are historians. And so, we look at the experiment from the following point of view. During the run, Arthur and Beatrice change their orientation, make a note of the results, have very precise atomic clock, and they record everything, and they record everything. After completion of the experiment, they come close together, they compare the data, and then they observe that indeed the correlation did change instantaneously. You cannot use it for practical faster than light signaling. But if you insist on thinking what did happen in the past, everything happened as if in the past something has really changed instantaneously.
Can I ask a question? What if you had a common clock at S, which simultaneously transmits the common time, which is a way of synchronizing their clocks without them having to, telepathically communicate? That then provides you a synchronization bit, which you then can tell whether things have changed.
And so what?
Well,
you don't even need that. You don't even need that because you can have, we have clocks good enough that they do not drift on the two sides for the duration of the experiment. So you don't even need, that. So I would like to conclude to try to answer the question, is it a real problem? I must say that this experiment took a long time for me to do, and it was my PhD thesis. It was very serious, and all along these years, from time to time, especially when the experiment was not working nicely, I was asking myself, maybe I'm doing an experiment on something which is not a true problem. And from time to time, I was discussing this with my friends. And it was close to the end of my PhD thesis in '82. We were collecting the final data, and a friend called me and said, there is a paper which is addressing the question. You should immediately look into it. It was in International Journal of Theoretical Physics, and then I found this quotation. It has not yet become obvious to me that there is no real problem. I cannot define the real problem, therefore I suspect there is no real problem. But I am not sure there is no real problem. And this final answer was given by Feynman in '82 in this paper, and with this I will not add anything. Thank you very much.
I think you've given a very beautiful account not just of the experiment but of the implications. But there is one point I'd like to take up, which is that what you call locality is really, I think, not one but two principles. One being that information cannot propagate faster than the speed of light, and the other that it cannot propagate backwards in time.
Yes.
So Einstein's dichotomy on the view graph that you showed actually leaves out that possibility.
Yes.
That there is some effect of the observation on the source.
Yes.
And it seems to me that that's what's an option which has not been explored as far as it might be.
In my naive understanding of special relativity, it's absolutely equivalent. I mean, as soon as I allow for a reaction between two events which are space-like separated, then I can find a frame of reference where it would go backwards in time or something like that.
Vice versa.
And vice versa. So it seems to me that it is really the same idea. The idea is there should be no connection between space-like separated events, and these can be either in the past or just outwards, I mean. That's my understanding.
Other questions?
Over there.
So, is it possible to, the violation of Bell, do the violations of Bell inequality also say that you cannot have a hidden variable theory like the Bohm hidden?
Oh, no, this is very interesting. Because, of course, Bell was very appealed by hidden variable theories. And he had first known of the famous and incorrect von Neumann's theorem that say there is nothing like hidden variable theory. And Bell noticed the existence of Bohm's hidden variable theory. So the first achievement of Bell in this domain, because he has achieved much elsewhere, but in this domain, the first achievement was to show how von Neumann's theorem is wrong. But then, thinking deeper, he recognized that in the Bohm hidden variable theory, you have a non-locality. That is to say, you have the so-called quantum potential. And for instance, if you want to describe Young's slit experiment, if you close one slit, immediately everywhere in space, and instantaneously everywhere in space, the quantum potential changes. So then he recognized that the Bohm hidden variable theory is a non-local theory. And of course, you are looking for a model fulfilling locality. So the Bohm's hidden variable theory is not a good model along this kind of demand.
The other argument that Bell used to make in private was, of course you can have successful hidden variable theories if you give up non-locality. Whenever you do a Monte Carlo simulation
Yes, oh yes, sure, yes.
of a quantum experiment, you are constructing such a thing.
Yes, you allow me to repeat it loudly because I heard this argument from Bell and I think it's very convincing. Whatever result you get from a theory, you can always mimic it by a correct Monte Carlo simulation.
Right.
Okay? And a Monte Carlo simulation is a classical hidden variable theory. The only point is that if you try to do it here, you discover that it is a non-local hidden variable theory. This is the argument, right? Yes, I discussed a lot with Bell of this stuff. Yeah.
Questions?
Nobody wants to know the demonstration of Bell's inequality? It's so simple. Okay, so Duncan Haldanes wants the demonstration. I'm not sure you are going to follow the algebra. It's so complicated, you will see. Take four quantity, x and x prime, and each of these quantity, x, x prime, y, and y prime, each of these quantity is either +1 or -1, okay? And forms a quantity xy minus xy prime plus x prime y plus x prime y prime. I can factorize and write it x y minus y prime plus x prime y plus y prime, right? And now, if they have the same sign, this is 0, and this is either +2 or -2. And if they have opposite signs, this is 0, and this is either +2 or -2. So this is + or -2. Now, if you remember the scheme where I have the A, B, A prime, B prime, etc., in fact, I can write A of lambda, A, B of lambda, B, etc., and the fourth set of things. And then when I calculate the quantity E, is just amount to doing an average over all this. And the average of a quantity with values which are either +2 or -2 can only be between +2 and -2. That's all. It's beautiful, right? Because it's so elementary algebra. Well, in the initial paper by Bell, it was slightly more complicated, but between you and me, a high school student can follow the demonstration of the initial. It's slightly more complicated, but it's not much more. It's beautiful because it's so simple. This puts the emphasis on another point. There are two ways of building a hidden variable theory to mimic quantum mechanics. The first one we already told is to build a non-local hidden variable theory. The other one that was advocated by Feynman is to use negative probabilities. If you allow this quantity rho of lambda, which is here, to assume negative values, then you can violate Bell's inequality, and this comes, for instance, in quantum optics by the fact that if you calculate the Wigner function, then you have a Wigner function with negative values. But honestly, I was lucky enough to discuss this with Feynman, okay? Honestly, as a naive experimentalist, I don't at all understand what means a negative probability. Because when I think to my experiment, it means that if an event happens with a negative probability, then this event has to be erased from the world. That means erased from the memory of my computer, maybe erased from the printed sheet of paper on which the result was already printed. So it's very hard for me to...
And that just gets to zero.
Yeah. So it's very hard for me to swallow a model with negative probabilities. Yeah.
Non-normalizable or otherwise strange.
Well, I leave it.
To something like that, right?
I leave it to smart theories, but I think that if somebody had come with a convincing solution of this type, I mean sophisticated mathematics, I mean the problem now is popular enough that there would be a consensus among, I mean I use an authority argument. I cannot judge myself, but I am deeply convinced that it would have been recognized by Bell himself or these kind of people. I know that, for instance, Whiteman in Princeton has worked on that for some time and tried to find if there were mathematical problem of this kind.
Isn't there a non-statistical scheme that in any given run can produce a result that is non-consistent with local reality?
You want to discuss the GSZ scheme? Well, I think, honestly, that it is not true that the GSZ scheme allows you to make a test which is not statistical, for the following reason. Well, let me first make an historical comment. In the first version of Bell's inequalities, you needed first to assume that for parallel polarizer, you have total correlation, 100%. And then, built on that, you derive an inequality. And then there was a big progress of the Clauser, Horn, Shimony, and Holt inequality that do not demand the initial assumption that you must first test perfect correlation for parallel polarizers. Now, for what I understand in the GSZ scheme, you are like in the initial version. That is to say, you must first check that you have perfect correlation between a set of measurements. Then, having checked that, then you do the test. So I don't think that it is true that it is not a statistical test. Because it's not only one measurement. It's one measurement having checked plenty of things before. So I would prefer a test of GSZ which can be phrased in the same way. That is to say, there is only one set of quantity I must measure. I put all them in a single expression, and at the end of it. You know, to test this S between -2 and 2, I don't have to invoke preliminary test or things like that. A single run, that's all.
Okay, there are no further questions. Let's thank the speaker again.